Okay, so here we have a problem dealing with blood types, and it's talking about how each of us has an A-B-O blood type, which describes whether two characteristics called A and B are present. Every human being has two blood type alleles, one inherited from our mother and one inherited from our father. Each of these alleles can be A, B, or O. The two that we inherit determine our blood type. The table shows what our blood type is for each combination of two alleles. We inherit each of our parents' two alleles with a probability of 0.5. We inherit independently from our mother and father. So here are the possible blood types: A, B, and O. And the alleles we have to inherit to get those blood types. And part A, we got that Hannah and Jacob both have alleles A and B. We're going to need to diagram the sample space that shows the alleles that their next child could receive. Then let's give the possible blood types that the child could have, and let's make a probability table for each blood type. Okay, so I'd recommend doing like a sample tree, or a probability tree, because I really like the way it shows like how all the combinations and all the possibilities could occur, and it does it in a pretty simple and easy to read way. So so we're talking about blood type, and when it says we inherit a one allele from each of our parents. So like let's just first look at like what we can inherit from Hannah. So that's what this first branch is talking about. Now, I'm just picking Hannah just because I could pick Jacob because it doesn't matter the order. It doesn't matter if I put Jacob first or Hannah first. This is just to show the possible combinations. But let's say we're talking about what we can inherit from Hannah first. And since Hannah and Jacob both have alleles A and B, their child can inherit either an A or a B from Hannah. And it says that each allele is inherited from our parents with probability 0.5. So the child has a 0.5 chance of inheriting either an A or a B from Hannah. Now let's look at what the child can inherit from Jacob. This breaks down into two events or two possibilities for each of these, because they could also then inherit an A or B from Jacob, given that they inherit an A from Hannah, or let's say that they inherit a B from Hannah, they could then inherit an A or B from Jacob still, because the combination here would be AA, here would be AB, it would be like a BA, and here would be a BB. Again, we could put Jacob first, because technically it doesn't matter. This is not about like time, what occurs first or second, because we're talking about a child being born. But in either case, they still have a 50% chance of inheriting A or B from Jacob along each of these branches. So the probability of them in getting combinations A, B, or BB, each of these are just 0.5 times 0.5 or 0.25. The probability of them getting A is 0.25. The probability of them getting AB is 0.25. And the probability of getting BA 0.25, BB 0.25. Now, this is going to be a little different than the actual blood type. Let me write that over in this last part. Because these are the alleles inherited. If they inherit an A and an A, they're going to have blood type A. An A and a B, they're going to have blood type AB. A B and an A, that's the same as an A and a B. Remember, the order doesn't matter. So they're still going to have blood type AB. And then B and a B, they're going to have blood type B. Now, so you can see that these two together, they're the same blood type. So let's make a table to make this more clear. Let's have blood type in the top row. Let's have probability bottom row. And so they could have a blood type A, blood type AB, or blood type B. The probability that the child gets blood type A is just at 0.25. The probability they get AB is going to be 0.5 because they can get AB in these two combinations, or 0.25 plus 0.25, so that'll be 0.5. And blood type B will be this last one, 0.25. And it does check out because these three possibilities add up to 1, which is what you want because this breaks down this basically shows the entire set of possibilities or the entire sample space, which has to add up to 1. Okay, now let's look at part B. Jennifer has alleles A and O, and Jose has alleles A and B. They got 2 children. What's the probability that at least one of the children has blood type B? Okay, so let's first just look at what the probability of one child getting blood type B would be. Because first we need to first know what the probability of blood type B is just overall, and then I can break it down into like 2 children. So let's use the probability tree again. I'm going to go through a little faster since we just did one. So let's talk about what the child can get from Jennifer first. The child can get, an A or an O, again with 0.5 probability. And then from Jose, the child can get an A or a B. Oh, I guess I might as well put an arrow there, A or B. Each of these again are 0.5. So this results, this is an AA, this will be an AB, this will be an OA, this will be an OB. And all these have probability of 0.25 still. They're all 0.25. Because again, 0.5 times 0.5 will across 0.25. Now, let's look at the blood types. Which of these results, in blood type B? 2 A's we found to be blood type A. An A and a B was AB. An O and an A and O, same thing, blood type A. O and a B or B and an O, same thing, blood type B. So this is what we're looking at. So they have a probability, one child just in general has a probability of 0.25 getting blood type B, just in general, just one child. Okay, so if we were asked what the probability that one child was to get one child were to get blood type B, it would be 25%. We're asking about 2 childs, but we're asking just at least one of them. So if we're talking about 2 children, and we're trying to figure out what's the probability at least one of them gets blood type B, there's a couple ways this can happen. You can have either the probability that both have, let's just say, have blood type B. Both children have blood type B, because that's at least one of them, of course. Plus, because we could also just have, let's say, child 1, plus the probability that just child 1 has blood type B, child 1 has B. Or we could just have the probability that child 2 has blood type B. There's three ways that you can have at least one of their children having blood type B. Either they both have it, or child 1 has it, or only child 2 has it. So both have it, only child 1, or only child 2. So we just add these 3 probabilities. Now, these ones we already found. well, actually, no, actually, let's actually not talk about it. Let me actually talk about this. The probability they both will have it is going to be 0.25 times 0.25 because remember they inherit, it's independent. The chance that whatever one child gets, whatever the blood type that one child gets is not going to change or affect the probability of the blood type that the second child will get. It has nothing to do with the probability of the other child. They're independent. So the probability that they're both going to have blood type B, well, using the multiplication rule, will be 0.25 times 0.25. Now the probability that child 1 will have it, is going to be 0.25, because that's child 1 having it, times the probability that child 2 will not have it. Since the probability of a child having it is 0.25, the probability of a child not having it is 0.75. And again, we multiply it because they're independent events. And then we do the same sort of logic for child 2 only getting blood type B, let's just reverse the order to make it consistent. Child 1 will not have it. That's a 75% chance that child 1 will not have it, times the probability that child 2 will have it. So 0.25. And now we just add all these guys together. Let's see what we get. Doing all my calculator, and we're gonna have a probability of 0.4375. Don't break on the pencil. 0.4375. And there we go.